In mathematics, an equation of multiple variables is going to give a relationship between 2 or 3 or 4 different variables. Now, in the idea of related rates, which is what we're going to be talking about in this video, what we're going to describe is not a relationship between the variables themselves, but a relationship between the rates that come out. So let me give you a specific example. I'm going to give you a word problem, and we're going to be interested in how one rate is related to a different rate. In this problem, I want to imagine you've got 2 different cars and they're both going off and they're driving. And the first of the car has gone and driven 0.4 miles east. And then you've got a second car that started at the same spot that you have here, but it's driving north and it's driven 0.3 miles north. Now, this is a picture that demonstrates some information about the world, and we can ask questions about how these are going to be related. And one way that we could ask a question is, what about the distance that goes between these 2 points? How far away are these 2 cars if they both have driven in this amount? There's this relationship D here. And I can find some equation that expresses this. This is just a right triangle. I can use Pythagoras. And I can claim that the distance squared here is going to be equal to the y squared plus the x squared. So this is just the Pythagorean relationship between these 3 different variables. And then, since I know what the car A is driven, the 0.4 miles, and I know what the car B is driven, the 0.3 miles, I can plug those numbers into my equation and I can get that the distance between them is going to be a half mile. All right, so this expressed the relationship, but not amongst the rates, amongst the original quantities, the x, the y, and the d. And indeed, this relationship was at this specific time when it was 0.4 miles and 0.3 miles. But I could also ask the question, what would this look like as a function of time? If I'm imagining that my car continues to move and my car B continues to move, how does my distance change as a function of time? So let me add some more information to this picture. I want to describe how it is that my cars are changing with respect to time. So what I'm going to say is that my car B is traveling north at 50 miles per hour and that my car A is traveling east at 60 miles per hour. So we have this specific time where there's this specific distance they've already traveled, but that they're going at some velocity, in this case the 60 and the 50 miles per hour. Now, if I think about this equation, which is an equation of t, and if I get rid of all of my other information for a moment, it's some function of t, so I can take its derivative. I can take the derivative of the left with respect to t, and I can take the derivative of the right with respect to t. And so I'm going to pop out and say that we've got the derivative with respect to t of the left and the right. Now, I can do this derivative. These are actually relatively simple functions. If I have the distance squared, then I'm going to apply the chain rule. And it's going to be twice the distance times d prime. And the same as we go along. So I'm going to say twice the distance d prime, twice the distance, but now it's x. So twice the x prime, and twice the y prime. That's applying the chain rule and the power rule to all of these variables to the power of 2. Now what's interesting about this equation that we have down here is I want you to note that it is relating the original variables, the d, the x, and the y. We can see that those are there, but it's also relating the derivatives of those variables. It's also relating the d prime, the x prime, and the y prime. If I'm really interested in the question, what is the rate of change of the distance between the 2 cars, I might be most interested in figuring out what the d prime is. Then what I can do is I can rearrange this formula, and by dividing out the 2d, I get that the d prime is just going to be equal to the x prime plus the y prime, all divided by the d, and I've canceled out the 2's. Okay, so we've got to this formula by taking the derivative of our original Pythagorean equation. So I want to focus this, but now I want to plug in my numbers. So let me keep that up there, and I'll remind ourselves that we had this scenario where we had the original y was 0.3, the y prime being the 50, the original x value, the 0.4, and the x prime, the 60. And so what we get plugging these numbers in is this expression, where for the distance as a function of time, I've put in the 0.5 that we computed previously. And then if I actually go into my calculator, I can decide that this number is going to be 78 miles per hour. So what we've accomplished is that I've figured out d prime of t, which is telling me that this distance, the distance between the 2 cars, the distance as a bird will fly, that is changing at this rate of 78 miles per hour. This is a derivative, it is a rate, it is a miles per hour, and we have managed to be able to compute that. All right, so the major steps in these related rate problems will be more or less the same, even if the specific picture is going to change. So the steps as I see it are, for a related rates problem, the first thing is, if I give you some word problem, you have to understand it. You have to be able to sort of visualize it. So the first step that we would always do is to sketch some picture of it, and that's what we did in this particular example. We sketched where car A was, where car B was, what this distance was, and we got this nice visual representation of it. And then after you have that nice picture, what you can do is you can try to find some equation that's going to be relating the variables that we're interested in. In this case, it was going to be this relationship that the d squared was the x squared plus the y squared that comes from Pythagoras. But for a different problem, with a different picture, the relationship between the variables might be somewhat different. But either way, you want to find some equation that relates those original variables. That's not quite enough because we want to be able to differentiate to get a relate. We want to relate our rate. So we're going to take the derivative of whatever we have, and that's what we did here, where I went and found that my d prime of t was some particular function. And then, after I've got my function, I'm not interested just in what the equation is. I want to know what it is at some specific values of data. And so I can go and sub in whatever the values, and that was how I eventually got down to the 78 miles per hour.